Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 19 of Algebraic Topology. Our today's topic of discussion is singular homology. We will start with the definition of singular homology and then we will continue with the dimension axiom for singular homology. What is singular homology? So as we know that what we have done in simplicial homology, so in simplicial homology we use the following steps to calculate the homology of a topological space. So we started from a topological space X and then we triangulated the topological space. So for example, if it was a torus, then we triangulated the torus. If it was a projective plane, real projective plane, we triangulated the real projective plane, and up to so on. So after triangulating the topological space, then we constructed the chain complexes and then we constructed the simplicial homology of that topological space. Okay. Now we are going to discuss another homology of topological spaces, and we will see that for example, for simplicial complexes, the singular homology and the simplicial homology, they give us the same answer. Okay. So in simplicial homology, what we have done is basically we dealt with simplexes. Okay, so that was the basic building block of our simplicial complexes, which is simplicial complex is a special collection of simplices. Now in place of simplices, now we are going to replace simplices with the continuous maps from simplices to the topological space. So once again, after triangulating a topological space, then we dealt with simplices and simplicial complexes. Now instead of simplices, we are dealing with continuous functions from simplices to the topological space. In simplicial homology, we use simplices as bases of the free abelian group. Okay, so in singular homology, we will use these continuous maps as bases of the free abelian groups. So that's the basic difference between singular homology and simplicial homology. So why singular homology? That's the question. So although we can compute simplicial homology, but computations can get very tedious. So for example, if you are trying to triangulate some complicated surface or some complicated topological space, then the triangulations of that could be many of them, and then it will be complicated to compute the simplicial homology. So we move to singular homology, which is relatively simple to compute, but when I'm saying relatively simple to compute, it means that if you apply the definition of singular homology, then it might not be very simple, but what it means is that there are some results which are derived from the definition of the singular homology, and those results will be helpful in computing the singular homology. So on the other hand, the computation of simplicial homology is very algorithmic. Okay, so we are basically dealing with some very combinatorial things, and so we can easily form codes, and we can use computer to calculate the simplicial homology for us. And in fact, there are many softwares that can compute simplicial homology for you, and so in that way simplicial homology is advantageous, but singular homology has its own reasons for existence. Before starting with our discussion of singular homology, let us review some previous definitions and results. So why we are going to need this? Because we know that we are going to deal with continuous functions from delta n dimensional simplex to this topological space X. So let us review what are these simplices and how we generate them and what are the elements of these sets. So the kind of points that generate an n simplex, so they have some certain condition that they should satisfy. And what is the condition? So a set of points, a set of m plus 1 points is affine independent if p1 minus p0, p2 minus p0, pm minus p0 is linearly independent subset of the real vector space Rn. So what does this condition mean geometrically? So it means that, for example, if I have 3 points p0, p1, p2, then these 3 points should not be collinear. Okay, so they are not allowed to lie on the same line. Okay, so similarly, if I have 2 points, then they should be different, up to so on. So in other words, we can say that these m plus 1 points should not lie on a m minus 1 dimensional plane. Okay, so so the planes have dimension. So plane means some geometrical object defined by some linear equation, but this is just a geometrical meaning. So if you are interested, then you can have a look in one of the reference books. But this is enough for us, that if we assume this definition, that a set of points, a set of m plus 1 points is affine independent if this set is linearly independent. And of course it is set of points in n-dimensional space, and if this set of vectors of Rn, p0, p1 up to pm, okay, so this is a set of vectors of Rn as well. So if this set of vectors is linearly independent, then of course this set is affine independent as well. But the converse is not true. For example, we can take p0, p1, pm. So one of these points, if one of these points is 0 origin of Rn, then these points will not be linearly independent, but these points can be made to be affinely independent. So let p1, p1 up to pm be a affine independent subset of Rn. So the convex set spanned by this set, denoted by square brackets p1, p1, p0, p1 up to pm, is called the M simplex with vertices p0, p1 up to pm. Okay, so what does this mean? It means that we are talking about the smallest subset of Rn containing these points, and that subset is convex as well. Or in other words, we can say that we are talking about the intersection of all convex subsets of Rn containing the points p0 up to pm. Okay, so for example, if I have 3 points, then for example, consider this triangle, then the convex set containing, so the smallest convex set containing this point will contain this line, and this line, and this line, and every line joining them. Okay, so it will contain all of these things, and so it is basically a solid triangle generated by these 3 points. And similarly, if we have 1, 2, 3, 4 points, and then the simplex, so the smallest convex set containing these 4 points will generate a tetrahedron in 3-dimensional space. So if m plus 1 points p0, p1, pm is affine independent, then each x, now we are going to describe what will be the elements, or an easy way of writing down the elements of this smallest convex set containing this point, or in other words, basically the M simplex. Okay, so basically M simplex. Now if p0, p1 up to pm is affine independent, then each element x in the M simplex has unique expression of the form. So now this is a simple way of writing down the elements of the M simplex generated by the points p0, p1 up to pm. So in other words, the smallest convex set generated by or containing elements p0, p1 up to pm has elements of the form. So ti, pi where the sum of ti is equal to 1 and each ti is greater than or equal to 0. So that's the form of the elements of M simplex, which is generated by the points P0, P1 up to Pm. Now for example, consider the simplex generated by one point. So this is a zero simplex and consists of only one point. Okay, so this is 1 point and this is a zero simplex. So a zero simplex. Now one simplex in other words, the simplex generated by points P0, P1. So what are the elements of this one simplex? So let's go back and see what the theorem says about the form of elements. So the theorem says that the form of elements will be T0, P0 plus T1, P1, where the summation T0 plus T1 is equal to 1 and Ti are greater than or equal to 0. So that's our theorem says. This theorem gives us the form of elements of the M simplex generated by the points P0 up to Pm. Okay, so this condition implies that we can take T1 to be equal to 1 minus T0, and so the form of elements become T0 plus 1 minus T0 P1. But then we also imposed the condition on the Ti's that all of them should be non-negative. Okay, so in other words, for example, if I take this T0 to be, for example, 2, then this T1 will be negative. And so this T0 should be less than or equal to 1 if I want my T1 to be positive or non-negative. Okay, so this T0 should be less than or equal to 1, and also the condition imposed on T0 as well is it should be greater than or equal to 0. So this T0 should be greater than or equal to 0. So this condition implies this, and so so this plus this, so this implies this condition that the form of elements of this one simplex is T plus 1 minus T and P1, sorry, there should be P0 here as well. So T P0 plus 1 minus T P1. Okay, and this T varies between 0 and 1. Okay, so this is the one simplex generated by 2 points. And what is this geometrically? Okay, so if you take 2 points, okay, so in any space, now when I take t is equal to 0, then you can see that for t is equal to 0 I will get the point P1. So basically this is the point t is equal to 0, the point P1. When I take t is equal to 0.5, then it will give me some other point, but eventually when I will take t is equal to 1, then it will give me P0. Okay, so this is the point when t is equal to 1. Okay, so starting from t is equal to 0, I will travel towards P0, and that will be the end point of it, and so it's basically a segment from P1 to P0. Okay, so a segment joining these 2 points, and it is a line segment. It is going to be a straight line because this expression is linear in t, so it's going to be a straight line. So this is the line segment. So line segment joining P0 and P1. Okay, and similarly we can see that a 3 simplex is a solid tetrahedron. So solid tetrahedron means the filled tetrahedron, everything inside the tetrahedron is also included in the simplex, and it will be generated by these 4 points. So our next definition is faces of a simplex. So if we have this 3 simplex, which is a tetrahedron, then it has many faces. So for example, consider this blue face, red face, this gray face, and this green face. Okay, so 1 2 3 4. So these are the four faces, or precisely speaking, these are the four two faces. Okay, so why I'm using the word two face? Because these are two simplices. So these faces are two simplices, so that's why I'm calling it's a two face. And similarly, we can define what is a zero face. So zero face is the points of this tetrahedron. So these four points are basically zero faces of this tetrahedron, and these one-dimensional simplices, these line segments, so 1 2 3 4 5. So these 1 2 3 4 5 6. So these six lines are basically one faces of this tetrahedron. Okay, so how we define it mathematically? So we have this set of points P1, P0 up to Pn, and this set of points is M simplex, and what will be the points of the face of this M simplex and the face opposite to Pi. Okay, so what will be the points? So let's say this is the point P0, P1, P2, P3. Now this blue face is the face opposite to P2. Okay, now this is the collection of all points where there is no coordinate of P2. In other words, this blue face is the two simplex generated by the points P0, P1 and P3. Okay, so the set of elements or the set of points of this blue face will be T0 P0 plus T1 P1 plus T3 P3. Okay, and of course the condition on T0, T1 and T3 is that their sum should be plus 1, and all of them should be greater than or equal to 0. So this is the set of elements which are points of this blue two face of this tetrahedron. So in other words, we can say that this is a face. Okay, so in this case this is M simplex, so in this case it means M minus 1 face. Okay, so this M minus 1 face has points of the form Tj Pj, j is equal to 0 to n, but I'm going to take Ti is equal to 0. So what is this I? So this Ti is this I is the same as this Pi. So in other words, when I'm taking the elements of the M minus 1 face opposite to the point Pi, then I should just take the coefficient of Pi to be equal to 0. So for example, in this case we took, when we are discussing the face opposite to the point P2, then we only take the coefficients of P2 to be 0, and so the elements will become T0 P0 plus T1 P1 plus T3 P3, and the sum of these coefficients is 1, and all of them are non-zero. Everything else remains the same, but we only take the coefficient of, in this case for example, P2 to be equal to 0. And similarly we can calculate the other faces, and in general we can define a K face. And for an integer k, one sometimes speak of a k face, namely a k simplex generated by k plus 1 of the vertices of this. So in this case we generated a 2 simplex, so this blue face is a 2 simplex or a 2 face of this 3 simplex. Similarly we can define, as I told you earlier, similarly we can define a 0 face and a 1 face. So 1 face means a face which is generated by 2 points, 2 generating points of this tetrahedron. So tetrahedron is generated by 4 points, and if you take any 2 points of them, then you will be getting a 1 face, and if you take one of the points, then you will be getting a 0 face. So what is a standard n simplex? So it is a n simplex which is generated by special points in Rn plus 1. So what are those points? So the points which are the coordinate points. Okay, so E0 has 1 at the first position and rest of them are 0. E1 has 1 as the second position and rest of them are 0. Similarly En is basically 0 0 0 and it has 1 at the last position. Okay, so there was no condition. There was no condition in the definition of simplex on P0, P1 up to Pm. There could be any points of Rn. Now, if we impose the following condition, that if you are in Rn plus 1, then take the following n plus 1 points, and the simplex, the n simplex generated by these n plus 1 points is called the standard n simplex. Okay, so for example, if you are in two-dimensional space, then the standard n simplex of this R2 is this line, which is the line segment joining 1 0 and 0 1. So we have already discussed that one simplex generated by 2 points is basically the line segment joining the 2 points. So basically the standard 2 simplex will be a simplex in R2 generated by these 2 points. And similarly, if you are in three-dimensional space, then we have 3 coordinate points. So in R3, so the standard 2 simplex will be basically this triangle. Okay, so this shaded triangle, in other words, this triangle and the points of this area region are also included. So basically it's a 2 simplex. Okay, so this triangle, this area which looks like a triangle at its boundary, so this is basically a 2 simplex, and this is a standard 2 simplex. Okay, so similarly, if you want to generate a 4 simplex, then you should be in so if it's n simplex, then you should be in Rn plus 1. If it's 2 simplex, then you should be in R3, and if it is let's say 4 simplex, then you should be in R5. So take 5 coordinate points of R5, and the simplex generated by them will be a 4 simplex. So what are the points of standard n simplex? So once again, let's go back and see what were the form of the points of a simplex. Okay, so a simplex has points of the form ti pi, where the sum of ti is equal to 1 and each ti is greater than or equal to 0. But if we take these pi's to be equal to these coordinate points, then the form of points become the following. Okay, so let's see the case of R3, and you should be able to see the general case from here. So in R3 we have the points, let's say, okay, so the form of the points of this 2 simplex in R3 will be T0 E0 plus T1 E1 plus T2 E2. Okay, so which is basically equal to T0, and what is E0? It is basically 1 0 0. So what is T1? It is basically 0 1 0. So what is T2? It is basically 0 0 and 1. So if you multiply them and then add them together, then you will get the points T0, T1, T2, and of course this element is basically element of a simplex generated by the points E0, E1, E2, and we have the following condition on these coefficients, that their sum should be equal to 1 and these ti's should be greater than or equal to 0. Okay, so so the standard n simplex has elements of the form T0, T1, T2, and the condition on ti's remains the same. Their sum is 1 and all the ti are greater than or equal to 0. So we can say that the elements of an n simplex in general are of this form, and the sum of ti's is 1 and all the ti's are greater than or equal to 0. So that's the form of elements of a standard n simplex. So notice that if we remove the condition ti greater than or equal to 0, then we get an affine hyperplane in Rn plus 1. Okay, so if you consider the case, once again let's go to R3. Okay, so in R3 consider this set of points T0, T1, T2 such that T0 plus T1 plus T2 equal to 1, and all the ti are greater than or equal to 0. So if I remove this condition, okay, so let's remove this condition. Now see what is this set. So basically it is set of points t0, t1, t2 such that the sum t0 plus t1 plus t2 is equal to 1. Okay, so you know it from the calculus that this is basically a plane in R3. Okay, so this is basically a plane in R3. Similarly, if you go to higher dimensions and then if you drop this condition that ti are greater than or equal to 0, then this is going to be a hyperplane. Okay, so a plane, if you are in Rn plus 1, then this is going to be a plane of dimension n. Okay, so in R3 you get a plane of dimension 3 minus 1. Okay, and in Rn plus 1 you get a plane of dimension n plus 1 minus 1, which is equal to n. So you get an n dimensional plane, and we call that as hyperplane. So a hyperplane is basically a plane of dimension n in Rn plus 1. So a standard n simplex consists of points of affine hyperplane lying in the portion of the space where ti are greater than or equal to 0. Okay, so as we have seen, what is a 2 simplex in R3? So it is going to be a triangular face. Okay, so this region, but this is triangle because we impose the condition that ti are greater than or equal to 0. So this implies this. But if we drop this condition, after dropping this condition, I will get this infinite plane. Okay, so so this infinite plane containing this triangle. Okay, so and so okay, so the plane containing two simplex. So it's a plane containing this 2 simplex, and so that's the plane that we get after dropping the condition ti are greater than or equal to 0. So in other words, this plane is basically defined by the equation t0 plus t1 plus t2 equal to 1. Okay, so that's the equation of this plane, and if we impose the condition ti are greater than or equal to 0, then we will get the following 2 simplex. Now given any affine n simplex, there is a canonical homeomorphism from the standard n simplex to alpha defined as the following. So in standard n simplex, we take the generating points to be 1, 0, 0 up to so on, and E1 to be 0, 1, 0 up to so on, and up to En is equal to 0, 0, 0 up to 0, 1. Okay, but if we take any points, okay, V0, V1 up to Vn to be the generating points of the n simplex, then what's the relationship between that any n simplex and the standard n simplex? So let's in particular let's consider this example. Of course it's a 2 simplex in R3. So in fact you can see that these points are basically coordinate points, so it is basically a standard 2 simplex in R3. Now what if I take my generating sets of the n simplex to be any 3 points? Okay, so let's say this is my first point, this is my second point, and this is my third point. Okay, so we are still in R3. Okay, so extend these x's. Now the condition on the coefficients is the same. Okay, so that is the sum of the coefficients should be equal to 1 and all the ti's are greater than or equal to 0. So what we are doing is that we are basically somehow translating this standard 2 simplex to the simplex generated by the points. So for example, let's say this is E0, E1, E2, and this E0 somehow goes to P0. So let's say this is the point P0, and this E1 goes to the point P1, this E2 goes to the point P2, so this is the point P2. Okay, so somehow, so this point is going to this point is going to this point, and this point is going to this point. So basically it becomes a triangle at here. Okay, so this is the two simplex. Okay, and this vector is basically this P1, this is P0, and this is P2. So that's what it means, that the relation between a standard n simplex and any n simplex. Okay, so since it is generated by any vectors, so that's why we are somehow translating this standard n simplex to this simplex. Okay, now we are going to need standard n simplexes when defining the singular homology. So but we should know the relation between any standard n simplex and n simplex. So let us start with our basic definition of singular homology, which is going to be our basic building block. So singular n simplex. Okay, so once again, in simplicial homology we consider just n simplexes, and in singular homology we are going to discuss and we are going to deal with singular n simplex. And we have already seen that what is going to be the basic building block. So it is basically a continuous map from this n simplex, standard n simplex. Okay, so this is a standard n simplex. So from standard n simplex to the topological space X. So if we have this continuous map, then this is called a singular n simplex. Okay, so why this is called a singular? Because we just imposed the condition of continuity, and it may or may not be smooth. In other words, this image of standard n simplex inside the topological space X could be very, very singular as well, because we haven't imposed the condition of smoothness, we just imposed the condition of continuity. So the continuous image of the standard n simplex could be singular, it could be of any shape. Okay, so let's consider an example. Starting from a very simple example of a zero simplex. So a zero simplex is basically zero singular simplex, in fact. So zero singular simplex is going to be a function, a continuous function from zero simplex to X, and we know what are zero simplexes. These are just the points. So basically a continuous function from a point to, okay, so let's take it P0, so point to, for example, this torus. So it's going to be just a point in torus. Okay, so similarly we can take, so let's call it sigma 1. Similarly I can take another continuous function taking this zero simplex. Okay, so let's use this square brackets just to make sure that this is a zero simplex. Okay, so let's consider another continuous function sigma 2 from P0 to another point, and we can also take another continuous function from the same P0 to some other point of the torus. And of course if you can keep on doing this practice, then you can easily see that I can define infinitely many continuous functions from any zero simplex to, for example, torus. And of course if X has infinitely many points, okay, then we can define infinitely many zero simplexes inside the topological space X. Okay, so that's a kind of different situation. Okay, so because in simplicial homology the zero simplexes, so they were always finite. Okay, so if I want to write down the free abelian group generated by zero simplexes in simplicial homology, then it was possible. But now you can see that these continuous functions, so there are infinitely many. Okay, so when we talk about the free abelian group generated by these singular n simplexes, then there will be many of them. Okay, so but it will not matter, because at the end we are going to take a quotient. Okay, so to define homology we will take quotients and then it will not matter. Okay, but this is the thing which is different from simplicial homology. And similarly we can see that what is going to be a singular one simplex. So we know that what is a standard one simplex. A standard one simplex is basically a simplex in R2. It's basically a line segment. So topologically speaking, this line segment is the same as the interval 0, 1 on real line. Okay, so these are just two line segments. We can easily define a homeomorphism from this to this, so they are homeomorphic. Yeah, so 0, 1 and this line segment, they are homeomorphic. Okay, so basically a 0, 1 simplex is going to be a path inside this topological space X. Okay, so it's just going to be a path from this point to this point. It may or may not be a closed path. So this is an example of one singular one simplex. And of course once again you can observe that I can define infinitely many singular one simplices. Okay, so it could be of this form as well. Okay, so something like this, or it could be of any form. So the only condition it needs to be satisfied is that this map sigma from this one simplex to the topological space X should be continuous, and once again the image could be of any form, so it could be of this form as well. Okay, so something like this. Okay, so it is also a path. Okay, so it may not be smooth, or it might have some singularities, but the point is it is just a continuous image of this one simplex. Now what will be our singular two simplices? So they are continuous images of standard two simplices. So consider this standard two simplex in R3. So these points V1, V0, V2 are basically, so if I call it X, Z and Y, then this is basically 1, 0, 0, and this V0 is basically 0, 1, 0, and this V2 is basically 0, 0, 1. Okay, so this is the standard two simplex in R3, and the continuous image of this standard two simplex could be, for example, of this form. Okay, and of course it could be of this form as well. Okay, so this one side, the second side, and the third side. Okay, yeah, so this is the image of this standard two simplex inside this topological space, or it could be of this form as well. Okay, so this is one side, this is second side, and this is third side. Okay, so it could be of this form as well. So this is one side, this is second side, and this is the third side. Okay, so it just have to be a continuous image. Okay, so what is the difference between singular and simplicial homology? So if we have an oriented simplicial complex and K be its underlying space, and let alpha be an n simplex in K, because K is simplicial complex, so it will have many simplices. Okay, so let alpha be just an n simplex inside K with vertices W0, W1, Wn. Then there is a unique linear map taking this standard n simplex to the space, so the underlying space of K. Okay, so for example, if we have this K simplex, okay, so let's say this is our simplicial complex, and this is the two simplex. Okay, so the underlying space of this is basically this space. Okay, so notice that I'm not drawing vertices. Okay, so this is the underlying space, and so we can define a function from this standard n simplex. Okay, so this is standard n simplex. Okay, so these are the coordinate points. So we can define a function from this to the underlying space, and of course you can see that this is going to be a linear map because it takes just the points of the standard two simplex to the points of this triangle with, inside the underlying space, and of course this is coming from this Two Simplex. Okay, so we can take a map sigma from delta n to the underlying space, and so basically this underlying space is a topological space, and this topological space has a triangulation. So what is the triangulation? So this K, the simplicial complex, is the triangulation of this topological space K mod. Okay, so basically we consider the homology of this space after triangulating using this simplicial complex K, and we consider the maps sigma from this simplicial complex and standard n simplex to mod K. And what do we do in singular homology then? We consider maps from delta n, so standard n simplex, to the topological space X. Okay, so instead of triangulating the space as K, okay, using this simplicial complex, and this is which is basically triangulation of the underlying space K mod. So instead of triangulating it, we are directly calculating, we are directly taking the maps from delta n, this n simplex, to X. So this is a rough difference between singular and simplicial homology. So let's go forward and see how to define the homology. And of course, to define homology we need to define what are n chains, or in particular what are singular n chains. Okay, so we have a topological space for any n greater than or equal to 0. We can define this Snx to be the free abelian group with basis all singular n simplices. Of course, if you remember what is Cn of x in simplicial homology, or Cn of k. Okay, so we usually used k for the simplicial complex, so Cn of k. Okay, so Cn of k is basically the free abelian group generated by n simplices inside the simplicial complex k, and in this case we define Snx of course to keep our differences. So we denote this n chains in simplicial homology with Cn, and the n chains in singular homology with Sn. Okay, so in this case this is a free abelian group generated by singular n simplices. And what are singular n simplices? Which are just the continuous functions from n standard n simplices to x, and we take s minus 1 of x equal to 0. Okay, so the elements of Sn of x are called n chains. So what is the form of elements of Sn of x? So these are going to be finite sums of the elements of Sn of x, and the coefficients are going to be from integers. So for example, one particular element will be of the form n1 sigma 1 up to so on n m, where m is a finite number, sigma m. What are sigma i's? So these are continuous functions from this standard n simplex to x, and of course this n is the same as this Sn, okay, because we are talking about n chains. Okay, so this is a continuous, these are all the continuous functions for I is equal to 1 to m, and this is one particular element from this set Sn of x, and these n i's are basically integers. Okay, so for a topological space, S1 of x is free abelian group generated by all paths in x. So since a path is a continuous function and delta 1 is homeomorphic to 0 1. Okay, so this is the same reason we have discussed earlier, that a one simplex is homeomorphic to a closed interval 0 1 on the real line. So basically S1 of x is basically set of all paths in x, because when we take a continuous function from this one simplex to the topological space x, then since this is homeomorphic to I, so basically we are talking about paths inside the topological space x. So S1 of x is free abelian group generated by all paths in the topological space x. So of course we are following the same steps as we did to define and to discuss the simplicial homology, and the next step, of course you can guess that we are going to define the boundaries. Okay, so before defining the boundaries of singular and simplices, let's see how we define boundaries for simplices. Okay, so we are going directly to the oriented boundaries. Okay, so let's define orientation on the simplex first. So an orientation on the simplex is just a linear ordering of its vertices. Okay, so if we have an oriented simplex, then how to define the boundary? We can define the boundary of an oriented simplex. Okay, so this is just one face. Okay, so how to define the faces? So the faces are basically, so for example, if this is two simplex and this is the orientation, okay, so E0, E1, E2. So we define the faces of this two simplex to be E0, E1. Okay, so this two simplex is denoted by E0, E1, E2. Okay, so this is the ordering. So as you can see that when I'm trying to calculate this face, then I just deleted E2. Okay, so similarly, if I want to calculate this face, then I will just delete E0. Okay, so basically from here you can see that it will become E1, E2. Okay, now if I want to calculate this side, then I should just delete E1 from here. Okay, so when I delete this E1, so it becomes, so after deleting E1 in this two simplex, so it becomes E0, E2. But the ordering E0, E2 is not right here. Okay, because it says that it's a one simplex from E0 to E2, but then you can see that it's a one simplex from E2 to E0. Okay, so we need to add some negative signs as well. Okay, so I need to reverse the order of this thing, so I need to multiply it with -1, so which means the order is reversed. Okay, so if it is E0, E2, then it becomes, with a negative sign, it becomes E2, E0. So negative sign represent that we are reversing the order. Okay, so if we have any standard n simplex, then in order to keep this orientation possible, okay, so I want to keep this orientation for the faces as well. So if we want to do that, then we have to add some negative signs to sometimes to reverse the orientations. Okay, so we have the following definition of the faces. If we have an oriented n simplex, and the faces of this are defined as -1 is to power I, E0, E1, E2. So when we are deleting the vertex EI, then I will add -1 is to power I. Okay, so let's see if this definition is compatible with our observation. So when I'm going to delete E0, okay, so when I delete E0, it becomes E1, E2, so which is just -1 raised to power 0 and E1, E2. Okay, so we are not adding any negative sign in this case. But when I'm going to delete E1, then I will get E0, E2, but then I need to add -1 raised to power 1. Okay, because I'm deleting E1. Okay, so -1 is to power 1, and so this is equal to minus of this thing, and which is very compatible with our observation. Then I should add negative sign in order to keep my orientations. Okay, so similarly we can calculate faces, oriented faces for other simplices. Okay, so in particular we have already discussed this example. Okay, so of this two simplex. So what about the boundary? Okay, so the boundary is going to be the union of all these faces. Okay, so the union of all these faces. Once again, let's consider the example of this two simplex. So what is going to be the boundary of this two simplex, or standard two simplex? If it is standard two simplex, then the boundary is going to be union of this oriented face, this oriented face, and this oriented face. So in other words, if these are E0, E1, E2, so it becomes, so after deleting, so okay, so this is the two simplex E0, E1, E2, so it becomes E1, E2 union, okay, so minus E0, E2 union E0, E1. So this is the oriented boundary of this oriented two simplex. Okay, so now let's define the boundary of a singular and simplex. Okay, so on the same lines we are just going to define the boundary to be as follows. Okay, so let's consider this picture first. So what do I need to calculate? So this is a singular and simplex, because this is a continuous image of this standard two simplex. Okay, now I want to calculate this boundary. Okay, so I want to calculate this boundary. Okay, so if I take the image of this arrow under sigma, then this arrow is basically this line, and if this is okay, so this is v1 v2. Okay, so this is the one simplex generated by v1 and v2. So what is this arrow? Of course this arrow is sigma of v1 v2. So the image of this boundary one simplex of this standard two simplex. Similarly, if I want to calculate what is this line, so this question mark is basically equal to, so the continuous image of sigma, continuous image of v2 v naught. Okay, so basically if I want to calculate the boundary, then I should just take the continuous image under this sigma. Of course, if I want to calculate the boundary of this sigma from delta n to this topological space X, so if I want to calculate the boundary of this singular two simplex, then I should calculate the boundary of this standard two simplex, and then take the continuous image under sigma of this boundary faces. Okay, so that's the strategy. So in general, if I have a standard standard n simplex, so v naught up to vn, so what are the faces? So the faces are going to be deleting this v naught, so it becomes v1 up to vn, and then I can delete v1 and it becomes v naught, v2 up to so on, and vn up to so on. So basically I will repeat, I will start from 0 and I will end at vn, so this will go on and it will go to v naught up to vn minus 1. Okay, so these are all the faces of this standard n simplex. So what should I do? I should just take the continuous image of each and every face, and collecting them will give me the boundary of this singular n simplex sigma. Okay, so let's define how to define the boundary of the sigma. So this is equal to minus 1 raised to power I. So this negative sign is again here just to make sure that we don't lose the orientation of so the orientation of the simplex. Okay, so the orientation of the simplex and the orientation of the faces should be compatible. Okay, so it shouldn't happen that the orientation of a face is different than the orientation of this face in the main standard n simplex. Okay, so this negative sign is making sure of that, and sigma restricted to this thing means that we have restricted the domain of this function. Okay, so how to restrict the domain of a function? So for example, in this case when we are discussing standard two simplex, so it is set of points which is contained in this shaded triangle. But if I, so this sigma is a function which will take each and every point of this shaded triangle to this shaded triangle. But if I restrict the domains, if I decrease the number of points in the domain from this shaded triangle to just this line segment, to just this boundary line segment, then I will be calculating sigma, but my domain will be this one simplex v1 v2, and the image of this will be one face after applying this sigma. Okay, so one face of this image. Okay, so this sigma restricted to v naught up to vi, and deleting this vi up to vn is basically the continuous image of one face of the standard n simplex v naught up to vn. And since I want this face, and this face, so I should add them in order to make sure that I'm collecting all of these boundaries. Okay, so basically for example, if I consider a two simplex, so for example in this case, so this case is so the boundary Okay, so the boundary of this 2 simplex, so this is going to be equal to sigma restricted to okay, of course minus 1 to the power 0, restricted to v1 v2, because I just deleted e naught, plus minus 1 raised to power 1 sigma restricted to v naught v2, plus minus 1 raised to power 2 sigma restricted to v naught v1. So that's how we define the boundary of this 2 simplex. And what is this element? So this element is basically this side. Okay, so this side. And what is this element? So this element is basically this side. And what is this third element? So this third element v naught v1 is basically this side. Okay, so that's how we define the boundary of a singular n simplex. Now notice that if we consider this portion, okay, so v1 v2, now the question is this a standard one simplex? Of course the answer is no, it is not a standard n simplex. So it is not a standard one simplex. So what is a standard one simplex? Let's go back to our definition of standard one simplex. It should be generated by 2 coordinate points in R2, so generated by 1 0 and 0 1. Okay, so this line segment from v1 to v2 could be a one simplex, but it isn't a standard one simplex. So there is a difference. Of course we know there is a difference between a standard one simplex and one simplex, because standard one simplex is generated by these 2 points in R2. Okay, so this line segment from 1 0 to 0 1. So so does it mean that this definition is wrong? Okay, so it doesn't mean that, because implicit in this discussion was the following thing. Okay, so what we do is basically we, instead of taking v1 to v2, we are basically considering a function from this standard one simplex to this one simplex v1 to v2, and then we are taking the image. Okay, so in other words, when I'm taking the image from this one simplex to this one simplex, okay, so I want to consider this. Okay, so I want this curve. Okay, so basically I want this line. So in order to make our definition compatible, so how did we define the boundary? So we just took this one simplex and take its image under sigma, and then I will get this, and take this element. But this is not a standard one simplex, so what we do is basically first apply, let's say this is epsilon 2 and epsilon 2 0. Okay, so apply this epsilon 2 0 first from this standard one simplex to this, and so first we apply epsilon 0 2. So this 2 means we are applying it on a 2 simplex, and this 0 implies that this is the face opposite to v naught. Okay, so first apply this epsilon 0 2 so that the domain is going to be basically from this one simplex, and then apply this, and so we can say that this sigma epsilon 2 naught is basically a singular one simplex. Okay, so what is a singular one simplex? It is basically a map. So what is a singular one simplex? A map from standard one simplex to the topological space. Now this epsilon naught 2 is basically a continuous function, and sigma is also continuous function, so the composition of these two is continuous. So this function is continuous. So it is this continuous function that we have in our mind when we are defining this thing. Okay, so this continuous function from the standard one simplex to this side of the boundary is basically our one face of the boundary of this singular 2 simplex. Okay, so in general we can write down the following argument. If we have this standard n simplex, so if we delete this vi, and then it will not be a standard n simplex as we have seen in this case. Okay, so if you delete v0 from v0, v1, v2, so if you delete this v0, it is not a standard one simplex. So what we do, we consider the following function ei n. So this n means we are considering, or we are taking the elements to a 2 simplex. Okay, so in this case this epsilon 0 2 is taking the elements to this 2 simplex. Okay, and this 0 means we are deleting the 0th phase. Okay, so in this case we are deleting the ith vertex, so it is basically epsilon n I. So it's taking this standard n minus 1 simplex to this n simplex, and it's taking basically these elements to these elements. So just like as we have done in this case, so this take this standard 1 simplex to this 1 simplex inside this standard 2 simplex. Okay, and so implicit in this definition is that in fact we are not considering these simplices, we are in fact considering some other standard simplices, and using these maps as well, but it will not disturb our calculation of the homology if instead of considering maps sigma epsilon naught 2, so instead of considering these we just consider sigmas defined on this way. So it will not disturb our calculations of homology. So we are just going to consider our definition to be this. So instead of taking sigma epsilon n i's, we are just going to consider sigma restricted to this. Okay, so there are some books, for example Joseph Rotman will consider this definition, but we are not going to follow that notations. So precisely speaking, the boundary of singular n simplex is basically this thing. Okay, so sigma epsilon I n belongs to this free abelian group. Okay, but we will use the following definition so to simplify the situation, as I said earlier, that it will not disturb our calculations of homology. For each n greater than or equal to 0, there is a homomorphism from this free abelian group Sn to Sn minus 1x. So how to define this? We have already defined what is the boundary of a singular n simplex. Okay, so that's how we define the boundary of singular n simplex. Now we can extend this function linearly. Okay, so what does it mean to extend this function linearly? So what are the elements of Sn of x? So the elements of Sn of x are of the form a1 sigma 1 plus a2 sigma 2 up to so on plus an sigma n. Okay, so extend linearly means, so now I already know what is going to be the image of sigma n partial n sigma 1. I know what is the image of partial n sigma 2. Okay, so I can use this definition to calculate these things. Up to so on, I know how to calculate partial n sigma n as well. Okay, so in general this n is different from this, so let's take it m. Okay, so I can calculate these objects, so the boundaries of sigma 1 sigma 2 up to sigma m. But if I want to calculate the image of any general element of Snx, so what should I do? So basically I should apply this on a1 sigma 1 up to so on an sigma n. Okay, so this is m. So this is basically equal to a1 partial n sigma 1 plus a2 partial n sigma 2 up to so on am partial n sigma m. Okay, so this is what it means to extend this linearly. Okay, so if we extend this linearly, then this is going to be a unique homomorphism. So this part uniqueness can be easily proved by taking let's say take another partial n such that the image of sigma i's remains this, and you can easily see that these two will be equal. So let's say this partial n prime is another homomorphism which takes these sigma 1 to by using this definition. Okay, so in other words, this image is basically equal to minus 1 raised to power I sigma 1 restricted to v naught v1 up to vi hat, so deleting this vi vn. Okay, so let's say partial n prime is another homomorphism taking sigma 1 to this and sigma 2 to using the same definition up to so on. Then we can easily see that these partial n and partial n prime must be equal. Okay, so we have a unique homomorphism which will take the elements of Sn of x to Sn minus 1. So why it is homomorphism? Because we define it to be homomorphism. We extended linearly. Okay, so that's why it is homomorphism. So if you are not convinced, then it is an exercise for you to check that this partial n is homomorphism. Okay, so homomorphism of these free abelian groups. Okay, and then just take another partial n prime such that the image of these sigma is defined by this, and then to show that they are the same. Okay, so once again I am leaving this as an exercise for you, in fact a simple exercise for you. Okay, so similar to the case of simplicial homology, these partial n's are called boundary operators, and sometimes we denote partial n x. Okay, because if you change this topological space x, then these boundary operators will be changed. So we have the following sequence of free abelian groups and boundary operators. Okay, so Sn x, so the elements of Sn of x goes to Sn minus 1x, and using these boundary operators. So as most of you can judge that where we are going from here, of course we want to check that if this is a chain complex or not. This is a sequence of free abelian groups with these boundary maps which are homomorphisms, so the only thing that needs to be checked is this condition. So that's what we are going to do next, is just to see that if this is a chain complex or not, and of course what we are expecting is that it should be a chain complex. Then we will be able to define homology from here, and that will be called singular homology. Okay, so that's our next result. So we want to show that this composition is 0. In other words, when we apply this partial n plus 1 on the elements of Sn plus 1x, and then apply partial n on those elements, then the composition is 0. Okay, so since these are homomorphisms, so I just need to define, I just need to prove the result for some generator of Sn plus 1. Okay, so I just need to take a sigma from Sn plus 1 of x, where sigma is basically n plus 1 singular complex. So I just need to prove result for this thing, and if I can prove this result for this, then it will be true for rest of them, because we defined these boundary operators to be so we extended so we defined it in a way that we extended them linearly. Okay, so that's why this is only true for this. So in other words, we want to show that partial n plus 1 of sigma is equal to 0. Okay, so as many of you can remember that we have done a similar proof in simplicial homology. Okay, over there we didn't use the notation sigma restricted to v naught up to vi, excluding this and going to vn. So instead of using this sigma restricted to this, we just used v up to vi excluded up to vn. And of course, when I'm writing this, I mean minus 1 raised to power I and summation, and I varies from 0 to n. Okay, so in simplicial homology, we have the boundary defined like this, and in singular homology we have boundary defined like this. So the only difference is that writing down this sigma restricted to this. And if you look at the proof of this result for simplicial homology, then you will realize that it's just a matter of writing down sigma restricted to this, and rest of the steps will follow the same. So that's why I'm leaving this as an exercise for you to complete the steps, or in other words, just add sigma restricted to this in the proof of simplicial homology, and you will get your result. So if we have a chain complex, then we can define the cycles and boundaries. Okay, so the group of singular n cycles in X is defined as, so this is a set of elements of Sn of X such that the image of those elements is 0. Okay, so Zn of X is contained in this. And similarly, we can define the boundaries, which are once again which lives inside Bn of X, and which are images of elements of Sn of X inside Sn. Okay, so that's how we define cycles and boundaries. And once again, using the result that if I take composition of any two consecutive boundary maps, then their composition is going to be 0. Okay, so using this result, this composition is 0, so we can prove that this holds. So of course Zn lives inside Sn plus Sn of X. Okay, so because this is the set of elements of Sn of X which goes to 0. Okay, so this Zn of X is set of elements of Sn of X such that partial n of X is 0. So that's why this must be a subset of Sn of X. Now the only thing that needs to be checked is that Bn of X is contained in Zn of X. So what is Bn of X? So Bn of X is defined as the elements X belong to Sn of X such that there exists Y belongs to Sn plus 1 of X such that partial n plus 1 of Y is equal to X. Okay, so in other words, set of elements of Sn of X which are images of some element of Sn plus 1 of X. So take an element from here, let's call it alpha. So take an element from here, and now I want to show that this belongs to Zn of X. Okay, so in other words, when we apply partial n on alpha, then we get 0. Okay, so since this alpha belongs to Bn of X, so this implies there exists, let's call it gamma. So gamma belong to Sn plus 1 of X such that this alpha is equal to partial n plus 1 of gamma. Okay, now applying partial n on both of these, so partial n alpha is equal to partial n plus 1 of gamma. Now we know that this composition is 0. Okay, so maybe we should write it down as like this. So we know that this composition is 0. Okay, so this is a 0 map, it will take every element to 0, so this is equal to 0. So this implies that partial n of alpha is 0, and which implies, so the image of this alpha, which is an element of Snx. Of course, if alpha belongs to Bnx, then Bnx is contained in Sn of Snx. Okay, so so alpha is an element of Snx such that partial n of alpha is equal to 0, so this implies alpha belongs to Zn of X. So we have the following image that the boundaries are contained in the cycles. So every boundary is a cycle, and these cycles are of course contained in these. So instead of C's, now we have S. Okay, so we have this picture from a simplicial homology, but we should replace these C's with S. Now on the same lines, now we have a chain complex, we have boundaries, we have cycles. We proved that boundaries are contained in cycles, so we can calculate the number of cycles which are not boundaries. So in other words, we can calculate this quotient. So number of boundaries which are not cycles, so we take quotient with the boundaries of these cycles. So this is how we define singular homology. And of course this is basically set of cosets, and so the elements of this can be written as z plus b n x, and where this z belong to, okay, so this is x, so z belongs to zn of x, okay. And these are the elements of this set, and we denote this as the class square bracket z, so this is the class of z. So next time we will continue with the singular homology, and for example we will prove what is singular homology of a point, and we will do some other calculations as well. So this is the end of the lecture. Thank you very much, and Allah Hafiz.